A field tank starts with 74 liters. Water enters, a leak removes some, and then a controlled drain joins 4 minutes late. We need the total elapsed time when the tank reaches 246 liters.
Here are the exact choices. Before calculating, notice that the question asks for minutes since the inlet began. That time starts at 0, but the drain's clock starts later.
The schedule makes the timing difference visible. The inlet and leak begin at time 0, while the drain begins at time 4. The signs tell us which flows add water and which remove it.
Let T represent the total minutes since the inlet began. Then the inlet and leak each run for T minutes. How long has the delayed drain been running?
My first impulse is to multiply every rate by T. That would make the net rate 18 minus 2 minus 7, or 9 liters per minute.
That shortcut treats the drain as if it began at time 0. But during the first 4 minutes, no controlled drain water leaves at all. We must give each process its actual active time.
If the observation lasts T minutes and the drain waits 4 minutes, then the drain runs for T minus 4 minutes. That delay is subtracted from its runtime, not from its rate.
Good, now translate each contribution separately. The inlet adds 18 T liters. The leak removes 2 T liters. The delayed drain removes 7 times the quantity T minus 4 liters.
We also cannot forget the 74 liters already in the tank. Initial amount plus all sign changes must equal the final amount, 246 liters.
Pause here and solve that equation before we continue. Keep the parentheses around T minus 4 until you distribute the negative 7.
Distributing negative 7 gives negative 7T plus 28. The positive 28 appears because subtracting 7 times negative 4 becomes addition.
Combine the time terms. 18T minus 2T minus 7T is 9T. Combine the constants. 74 plus 28 is 102.
So the balance simplifies to 9T plus 102 equals 246. Subtract 102 from both sides.
Divide 144 by 9. The elapsed time is 16 minutes. That is longer than the 4-minute delay, so using a positive drain runtime is consistent.
Let me verify it with the actual flow amounts. In 16 minutes, the inlet adds 18 times 16, or 288 liters.
The leak also runs for all 16 minutes, so it removes 2 times 16, or 32 liters.
The drain begins after 4 minutes, so it runs for 12 minutes, not 16. It removes 7 times 12, or 84 liters.
Start with 74, add 288, subtract 32, and subtract 84. The result is exactly 246 liters.
So choice C, 16, is correct. The answer represents the full time since the inlet began, not merely the 12 minutes during which the drain was active.
Why would using 7T for the drain fail? At 16 minutes, it would claim the drain removed 112 liters, 28 liters too much.
That extra 28 is exactly 4 minutes of drain flow at 7 liters per minute. The algebraic correction and the real-world timing tell the same story.
A useful general rule is to draw a tiny schedule whenever processes start at different times. For each row, multiply its signed rate by the time that process is actually active.
My 3-step recap is: define the total elapsed time, translate every process with its own runtime, and check the final units and amount in the original situation.
This method works for tanks, workers, machines, travel legs, and any overlapping rate problem. The key is not just the rate. It is the interval during which that rate applies.
The delayed drain runs for T-4. The tank reaches 246 liters after 16 minutes, and the correct answer is choice C.